Okay.
All right, so we're very pleased to be hosting today Professor Andrew King. He's Professor of Astrophysics at Leicester, where he's also the head of the Theoretical Astrophysics Group. He's also Deputy Editor-in-Chief of FMNRAS, a monthly notice of the Royal Astronomical Society. So he's a busy person. He goes to other places, like he said, Amsterdam, for example, right now. I'll go very quickly through a CV. He got his PhD at Cambridge under the supervision of George Ellis, where he also worked with Stephen Hawking. Afterwards, he went to UCL in Hamburg, and then he was elected at Leicester, where his career evolved. Since then, he's also been visiting professor at the Observatory of Paris, Amsterdam, Leiden. Please correct me if I'm missing something out.
Yeah,
is that right? And in 2014, he got the Eddington Medal of the Royal Astronomical Society. So he's, what I know him for and what he's known very well famous in the galaxy evolution community is his theoretical work on the M-sigma relation, prediction of the M-sigma relation with the correct slope, and also on models of winds, AGN winds that are energy conserving and that solve some of the problems that winds used to have, and other things. Today he'll be talking to us about dwarf galaxies and the black hole scaling relations, and we're looking forward to his talk.
okay, you want me to start?
Yes, please.
Okay, so I'll play my slides. So everything still okay? Good?
Yeah.
Right, so thank you very much for the invitation. I wish I could be there in person. Athens sounds particularly attractive right at the moment after, I think my partner and I, he's actually in the room now, my partner and I realize it's 3 years since we had any sun because we had bad luck with a holiday previously, and then of course last year nothing happened, and it feels like forever. So I've never been as pale as I now am. So anyway, so I'm going to talk about dwarf galaxies and the black hole scaling relations. So let me start by just very briefly saying a little bit about galaxies. We're all, I think, probably familiar with the idea of spiral galaxies, which are, our own is one, we live in it. And there's most of the galaxy is a rather flat disk with spiral arms, but there's a central bulge in which the stars are more spherical, their orbits are more spherical. Those are thought to result from minor mergers with other galaxies. So they've captured stars into those orbits. And right in the very middle is a very large black hole of around 4 million solar masses. And of course, you will all have heard that Reinhard Genzel and Andrea Ghez, both good friends of mine, both recently shared half of the Nobel Prize for measuring the mass and actually proving that this thing was a black hole. You can't really prove anything in physics, but getting it to the point where it's very hard to think of anything else that it could possibly be. So that's a spiral galaxy, and the important thing is that the bulge consists of older stars than the rest of the galaxy, and they have a typical velocity dispersion, which I'll call sigma, and that it accounts for most of the, more or less all of the stars behave as though they were a thermal distribution with a temperature given by sigma squared. So sound speed given by sigma. So the other extreme is an elliptical galaxy, which I made a cartoon of below. And that kind of galaxy is effectively all bulge. It doesn't have the flat disk, and it has a spheroidal component with older stars, all older stars again. And it has a velocity dispersion which characterizes it. And it's probably the result of mergers of galaxies which have left, instead of leaving a nice spiral where something has joined the galaxy in an orbit, these have actually made major mergers and messed each other up. And so the resulting galaxy is all bulge and is a spheroid. I'll call these things spheroids from now on. And the really extraordinary thing that happened around the turn of the century is that people realized when they measured the masses of the supermassive black holes, which appeared to be there in the centers of all of these galaxies, is that when they plotted the masses against the total mass of the galaxy, or at least the mass of the bulge in the case of a spiral galaxy, but the total mass of an elliptical galaxy, those two quantities seem to be proportional to each other. The bigger its black hole. And even more strange, the plot on the right-hand side here, the velocity dispersion, like if you like, the sound speed of the stars that are moving around in the thermal distribution in the bulge of a spiral or the hole of an elliptical, that velocity dispersion also correlated quite well with the black hole mass. And the really extraordinary thing then is that tells you that the galaxies know about the central supermassive black hole. They know it's there, and they have properties that are closely related to its mass. And it cannot be directly gravitational, clearly, because the black hole is so small in mass compared with the galaxy. Its sphere of influence is just a few parsecs, perhaps, or tens of parsecs, something like that. So there are two competing theories for this. The one which, as you'll see, tends to win out is that this is the result, this correlation is a result of feedback. That is, the supermassive black hole affects the bulge and it stops growing when something happens. When it reaches a certain mass, it affects the galaxy in such a way it can't gain any more fuel and it stops growing. But the other theory, which I will talk about, is what we call assembly. That is, galaxies have merged, and as they merge together, their masses get bigger, but the central black holes find each other. They're able to, they do a sort of random walk, but they are gradually dragged into the center because they raise tides of stars behind them, and they spiral inwards because they behave as though they're very heavy, and they eventually end up in the middle of the galaxy. So those two pictures are what I'll talk about. What do we know? Why is feedback a plausible option? And the answer is, well, if you look at the amount of energy that was released as the black hole grew, remember, gas fell into the black hole to grow its mass, and we know from the Saltan relation that's how most of its mass was gained, at least at low redshift. And for a typical 10 to the 8 solar mass black hole, the amount of energy that's been released as radiation initially is about 10 to the 61 ergs. Now that you might not have a feeling for what that means, but if you compare it with the binding energy of the bulge of the galaxy, so the stars are running around at a few hundred kilometers a second, so typically about 200, and their mass is quite high. It's 10 to the 11 solar masses, so 1,000 times bigger than the black hole. But if you put those two numbers together, the binding energy, m sigma squared, of the bulge is only 10 to the 58 ergs, so 1,000 times less than the energy that the black hole released. So if you think of this like building a galaxy is like building a house, building a galaxy with a black hole in the middle that's growing is a bit like building a house with a bomb in the middle waiting to go off. If the bomb goes off and releases all its energy, 10 to the 61 ergs, it could in principle destroy the galaxy, just spew it out back into space. So I think the conclusion I would draw from that is that it's very hard for a galaxy to not be aware, at least in some sense, that there is a black hole in the middle. And there is no other obvious, easy way because the black hole mass is small. It's its binding energy that is big. So feedback is the main way that the galaxy knows that the black hole is there. So how do you communicate that energy? There are two main ways. The most obvious one is that when gas falls into a black hole through an accretion disk, it releases energy as radiation, electromagnetic radiation, so X-rays, gamma rays, all the spectrum, electromagnetic spectrum. And that is where most of the energy comes out, at least initially. So if that is able to push gas around, and we know it is quite easily able to push it around, you could imagine that would sweep gas out of the galaxy and perhaps slow down the growth of the central black hole. But you can see, actually, if you do a very simple calculation, if you sweep up a shell of matter and push it away, even though its mass remains constant, it will spread so much more thinly that eventually it becomes transparent. And that means that feedback won't really work. And put bluntly, we can see the center of most galaxies. We can see the active nucleus in there at most wavelengths. So it's rather unlikely that direct radiation pressure is at issue here, because that would mean we wouldn't see the central black hole. Although you can imagine situations where we might not see it for a bit, and then we eventually do see it. But probably it's not the main way that your feedback is being communicated. The other way, which is, I think, is very likely, is that there's mechanical feedback, that there's some kind of mechanical agency, some kind of matter, rather than just radiation, is interacting with the radiation of the matter of the galaxy, the stars and the gas in the galaxy, particularly the gas. There are two types of this. There's jets, that is narrowly directed streams of matter, or you could have quasi-spherical winds. And both are likely to be important, but the winds are more likely to have an effect. For one reason, they hit everything in their path. They don't just hit a few things. Jets, if they collide with a small part of the gas in the galaxy, as we'll see, that you get shocks in that kind of situation. If those shocks cool down, it means the jet will go through like a laser pointer. So the famous analogy is you can't warm up a lecture theatre by waving your laser pointer around. And the same thing will be true here, that the jets, particularly in that situation, would just make a hole and leave. So wide-angled winds, things that are nearly spherical, they're going to hit most of the central galaxy bulge, which is where we want the action to occur. So that's the most likely thing. And it's strongly confirmed by observations. And this goes back to quite a long way. This is actually not the original discovery, but there were earlier discoveries. In fact, Ken Pounds, who is the first author of the paper on the page there, came into my office in 2002, and he said, I've found this Seyfert galaxy with a really strange emission line. And he drew it on the whiteboard, and it had this characteristic shape. It had an emission line and then a blue shifted absorption line just to the higher side of it, higher energy side. And I said, oh, Ken, that's a P Cygni profile. And he said, what's that? Because he was not a stellar astronomer. He'd always done extragalactic things, and P Cygni profiles were not a thing that he'd come across regularly. But I said, it's simply that means there's an outflow. You see stuff coming towards you, blue shifted, and that is absorbing, but stuff coming out from the sides of the object, they don't have bright light behind them, so they look in emission. And so you see an emission line and a blue shifted absorption. But what was instantly obvious, looking even at the whiteboard, is that the way he'd drawn it, the blue shifted absorption was about as far away from the emission line as its own width. And that means that the outflow velocity had to be about 10% of the speed of light. There was no way out of that. And I said, well, it must have an enormous effect. If that wind has any amount of mass in it, it must have a huge effect on the galaxy. And then Ken asked another question, or made another statement, which is that host galaxy, that's not something we AGN people are usually very interested in. And of course, this was the moment where all that began to change. You could be interested in AGN because they were black holes and they were bright and they were doing exciting things. but the idea that they interacted with their host and did things to them was relatively new. But what we now know is that blue shifted absorptions like this are now seen in nearly all, a very large fraction of local Seyfert galaxies, for example. And they are pretty much, you can take them as more or less universal, and they all have these high speeds of about 0.1 C. So what's going on there? What I think must be happening, and all these ideas sort of came together very quickly, is that if you imagine you've got a black hole that's accreting from an accretion disk, and the black hole's the little black dot in the middle of the screen there, and the disk is the red line across the middle. So as stuff comes in and it gets nearer and nearer to the center of the disk where the black hole is, it's getting hotter and hotter, and it's emitting more and more radiation, more and more luminosity. And if it's trying to get there with the Eddington accretion rate, then it's actually trying to emit the Eddington luminosity, which says directly that radiation pressure is challenging gravity. And you can imagine solutions, various ways of dealing with that, but the most obvious one, which is in the original paper by Shakur and Sunyaev, is that the accretion disk blows stuff away progressively. That is, if there's too much matter at large radius, it blows a little bit away because the accretion energy isn't so large there. But as you move in, the amount of energy you get from each gram of material that's accreting gets bigger and bigger. And so you blow more and more of it away. So the accretion rate decreases into the center of the disk, and it blows away this wind roughly spherically. Because the gas doesn't know, it knows it's rotating, but it's not rotating so fast, and it doesn't know it's not supposed to go in certain places, so it goes more or less isotropically. In the very middle, and this is relevant to those of you who are interested in ULXs, in the very middle, it's quite difficult to have gas blowing right along the axis of the accretion disk, because it would have to have lost every single little bit of angular momentum, and that's very difficult to arrange. So you've got this wind blowing out in all directions, and it's quasi-spherical. And if you think of it as around the accretion rate as being close to the value that would give you Eddington luminosity, you can easily show that its optical depth to electron scattering is about 1. That is more or less the definition of the Eddington luminosity. And that tells you that if you've got optical depth 1, photons take about 1 scattering to escape. And when you scatter, electron scatter a photon, it's got an equal chance of going forward or backwards. And that means that on average, it gives up all its momentum, because the momentum is divided into forward and backward equally. And so effectively what happens is that the photons give up their energies mv, their momenta mv, and so all of the energy, the momentum that came in, which was m dot v, m dot was the amount of mass that came in, v is the speed it's going out with, that must be just the Eddington momentum. It must be just what the light gives it before the light escapes to infinity. And so m dot v should be about L Eddington divided by C, which is that equality down on the right-hand side. And that does seem to be obeyed by these, they're called UFOs, incidentally, these P Cygni winds, they're called UFOs. And if you take that equality, m dot v is L Ed over C, you can very quickly work out what the speed v will be in terms of quantities you know, and you find very quickly that v over c is about the accretion efficiency. That is the amount of energy you get for accreting each gram, and that's a number like 0.1. And so v then turns out to be about 0.1 c. So that's where that came from. And we knew all of that very quickly, which gave us a lot of confidence that this was about right. So the question is, how does that gas that's flowing out is being pushed away very violently from the black hole, but eventually it's going to hit some interstellar gas, and because it's clearly highly supersonic, there must be shocks. That is, there's going to be a reverse shock which will tell that gas to slow down, and there'll be a forward shock telling the interstellar medium to start moving outwards. So it's the reverse shock that takes away most of the energy. And there are two possibilities for what then happens. If the gas that you've shocked, and particularly the reverse shock, where you've slowed down the wind from the black hole, if that gas cools very quickly, that is, it cools before it's managed to flow the same distance again, something of that order. So if the cooling time, the radiation cooling time is short compared with the flow time, then it will have lost nearly all its energy, but it will just have what's left as its momentum. It can't get rid of that. And so it will simply be pushing with momentum into the interstellar medium outside it. And that's often called momentum-driven flow. There is another thing that's called momentum-driven flow that is completely different physics. It is to do with galaxies, but it's to do with dust. And sometimes that's also given the same name, which is very confusing. But that's what I shall use momentum-driven flow to mean, that the radiation from the black hole has all managed to escape, and the wind has shocked and lost everything it can except its own momentum. The opposite limit, when the shock just does not cool, so it's adiabatic, means that all of the energy that was originally in the radiation, or at least a very large fraction of it, can be used for driving as well as the momentum. So that's much more energetic. That's so-called energy-driven flow. And that means that the thermal pressure in the gas will be bigger than the ram pressure. The gas is heated up and gets hot and wants to expand. And the question is, which case are we in? And I can remember sitting in an office in Center for Astrophysics at Harvard, shortly after I'd gone there for a visit, shortly after Ken's famous contribution, coming and telling me about these UFO things, which they weren't called UFOs then, but this strange wind, and wondering what made them cool. I had a good reason for wanting them to cool, and it took me about a week to realize that if I tried all the things like free cooling, Bremsstrahl and so on, those don't really work. But what did work, amazingly, is the fact that the thing that keeps the shocks cool is that there's a quasar in the middle that's very hot. And you would think that would have the opposite effect, but no, it doesn't. This is something that Jerry Ostraker and collaborators had pointed out before. The inverse Compton effect of the quasar radiation field is quite powerful, because although the quasar is a hot object and radiates X-rays, its temperature is 10 to the 7 degrees, that's an X-ray temperature, whereas the shock temperature, which is given by taking 0.1 C and squaring it, is far higher. It's more like 10 to the 12 degrees. And so the Compton cooling, the Compton radiation field, if it has enough photons in it, will be very effective at cooling the hot gas that's shocked. And indeed, you can show that that's true, at least when the shock is very close to the black hole. The shocks do cool, and so the initial expansion into the bulge gas of this wind is driven simply by the momentum. And so I call that the bomb is disarmed. You haven't used all the energy, you've just used a certain amount, a little bit of it, very small part of it, in fact. So as I've said already, you can get the velocity of a momentum-driven wind by equating the momentum, two momenta, and you find you get 0.1 C. From the mass outflow rate, this is something Ken had already done, the mass outflow rate you can find because you measure its velocity and you measure the X-ray ionization parameter, the thing that tells you you've got a highly ionized ion, for example, tells you that the combination of the luminosity and the combination nr squared, where n is the number density of the gas and r is its current radial position, that is a known quantity. And so you can use those two things together to work out the outflow rate in mass grams per second. And when you stick them all together, what you find indeed is that the energy is a small fraction of the energy. The energy coming out of the black hole is L Eddington per unit time, but the energy being used to drive the gas layers away, push the bulge gas out, is only a half m dot v squared. And as you see, you work it through the algebra, it's only 5% of the total energy left that the bomb has in it. So 95% has been radiated away and didn't do anything very much. So in the momentum-driven case, you're just pushing gently. And so what you do, in fact, is sweep up the gas, and you can see there's the quasar in the middle is the thing with all the star-like thing. The green narrow thing is the shock, the wind which has been swept up into a shock. Remember, the wind was shocked as it hit the bulge gas outside it, but it's all piled in and it's ended up in a very narrow layer, very thin layer, which is pushing, but it gets heavier, denser and denser. The blue region is the shocked interstellar gas that's just started moving, and the red region outside the whole thing is interstellar gas that doesn't realize that there is a shock coming its way. It's still there, not moving. And so you get this kind of onion skin effect with the quasar in the middle, the shock that's moving out, and then the shocked interstellar gas trying to move out a bit too. Well, you can work out what's going on now quite easily. Because the interstellar medium is moving around with the stars, it has a constant velocity dispersion sigma 2. And so there's a Kepler-like relation. GM over R is, roughly speaking, sigma squared. There's a factor of 2 in there. And there's a gas fraction because some of the stars, not all the mass is in stars, most of it is stars, but a fraction of about 10 or 20% is gas. Let's assume they're proportional. And so you're sweeping up that gas mass into a shell, and you can ask, what's the equation of motion of the shell? So Newton's laws tell you that the mass is growing. So this is an inverse rocket problem. If you've had to do rocket problems as an undergraduate, the rocket loses mass. This is something that's gaining mass. So d by dt of m of r times r dot is resisted by gravity, so partly the black hole m and partly the swept up mass, the m total, that's 2 sigma squared r over g. And that must equal the ram pressure, which is L ed over c. So this incredibly simple equation, and you can solve that. I'll put it in a different form. First of all, put all the sigmas in using m, the relation between the mass per within radius r, the gas mass within radius r, that's proportional to sigma squared, and the total mass and so on is m of r. You put all those things in, you get the equation at the top, which is a second order equation. You can actually, oh yes, and I've isolated a constant on the right hand side. So you've got a first derivative of a second derivative, and then a term that's in R, and then on the right hand side there's a constant, and all those things are known, and all the other things apart from the black hole mass and the velocity dispersion end up in this thing called m sub sigma, which has the dimensions of a mass. So it's fg kappa over pi g squared sigma to the 4th, and it is a mass. You can integrate that equation if you multiply it by r times r dot, because the first term is x times x dot, if you like, where x is r times r dot. And so you can integrate it like that. And if you then look what happens at large R, there are two cases. If m is smaller than m sigma, all the terms on the right-hand side, apart from the constant, are negative. And so that means that as you go to larger and larger R, eventually you won't get a solution. The left-hand side is positive definite, and the right-hand side becomes negative eventually at large R. And that tells you that the thrust, the momentum from the black hole wasn't enough to lift all the swept up gas away. And that's characteristic of momentum-driven outflows, that they're not very good at lifting things. So on the other hand, if m is above m sigma, for some reason, we don't know what it is yet, if m is above m sigma, then you can see on the right-hand side, the second term is now positive definite. And at large R, the two terms which have R squareds in front of them will be equal. And so you blow stuff out at a speed √2 times sigma. So two very different cases. So what is m sigma? Because I can remember doing that algebra or something like it and thinking, well, this m sigma might be the m sigma mass. But I have no control over this. It has no free parameter in it. The gas fraction is pretty well fixed. Kappa and G are just constants, and sigma is sigma. And you work it out, and amazingly, it is about right. It's 2×10⁸ solar masses for a velocity dispersion of about 200 kilometers a second. And it goes through the points, more or less the right slope. You might say the isothermal potential is a bit simple. There are more sophisticated versions, for example, the cosmological one, NFW, Navarro, Frank and White, is often used. It turns out, and that's this paper by McCullin and McLaughlin there quoted, that you get very similar answers as you must do if you simply take the peak velocity rather than the average velocity dispersion. They predict a favored peak velocity in the galaxy. And that, if you use that as a proxy for sigma, you get more or less the same relation. So this thing doesn't seem to depend very strongly on the exact form of the potential. So I've got so far gas being driven out, but not eventually getting out if m sigma is too small. So if I haven't grown my central black hole to that mass, I still haven't really explained the m sigma relation. I've got something that's very suspicious, looks just like it. But why does it, is it the mass things tend to? Well, the answer is once you reach m sigma, what you can show very simply from the equation of motion for the momentum-driven flow is that R can exceed a certain radius at which the photons are able to cool. There are enough photons to cool the shocks. So we call that the cooling radius, and it's about typically 100 parsecs, something like that, 200. Once you get m bigger than m sigma, R can exceed the cooling radius. And so at that point, remember what was important about the cooling radius is that the shocks cooled. The wind shocks were cooled inside that radius. But once you get the shocks outside that radius, there are too few photons to cool the electrons and therefore the protons. The shock no longer cools. So we're now not in the momentum-driven regime. The shock is now adiabatic. And all of its PDV work, all of the pressure work will now push the gas. So the equation of motion now contains the total post-shock pressure, not just the ram pressure of the wind. So the bomb goes off. And if you now eliminate between the two equations, amazingly, you can get this horrible-looking third-order equation for actually the contact discontinuity. That R is the radius of the boundary between the wind coming from the black hole and the swept up interstellar medium. And that satisfies that third order equation. I remember looking at this and feeling a bit, this is going to be tricky, but realizing it had a constant velocity solution. So if you take the velocity to be constant, r dot is a constant, then you can solve that equation very simply. And it shows you that there will be a constant outflow velocity of around 1,000 kilometers a second, typically. And that mathematically, if you analyze that equation, which you can do various ways, that horrible third order equation, you can show that all solutions tend to that constant velocity solution. It's an attractor. So the supermassive black hole mass has been set to be equal to the m sigma value. Why have I done that? Well, because this velocity is so high that you're clearly sweeping away all the rest of the gas. All of the rest of the gas will be blown away and you will not be able to grow the black hole anymore. And so m sigma really is up to a little bit, because there's a kind of gap between reaching the value where the shocks move out and actually finally sweeping everything. M sigma is really more or less exactly what the black hole will reach in this kind of picture. So this removes all the gas very quickly. The galaxy becomes red and dead, and you see all these high velocity outflows. Amazingly, they're not seen, you would think they'd be seen in X-rays or something. They're actually seen in molecular lines. And the reason is the ionization equilibrium of that gas, even though it's very high speed, is such that it has to put a large amount of the gas into a very cool phase. And so most of it ends up as molecular gas. And they come out with the total energy. The flow energy must be now the total energy that's being emitted by the black hole. And remember, that was only 5% of the Eddington luminosity. And so you can now check, this is a good check on the whole thing, what is the kinetic energy of the molecular outflow? And indeed, they are a few percent of the Eddington luminosity. The mechanical luminosity is a few percent of the Eddington luminosity of the central black hole. So all of that seems to be quite consistent. So here we have the m sigma relation, but what about the relation between the black hole and the total bulge mass, which is about a factor of 1,000? Well, in the feedback picture, this is actually a coincidence of two relations that are parallel. The Faber-Jackson relation, which had been known for a very long time as originally just a luminosity correlation with sigma to the fourth, that tells you that the bulge mass goes like sigma to the fourth. It's found observationally, but actually it's not a coincidence that it is sigma to the fourth, because the basis of Faber-Jackson is actually momentum driving by stars, which are driving around the interstellar medium. So both as supernovae and as stellar winds, they're putting momentum into the interstellar medium, and that's why you get that relation. So there is, in addition to the m sigma relation for the black hole and sigma, there is a relation between the stellar mass and sigma. And so those two things are parallel, and that means that they're proportional. And it's often said that this is an acausal relation, although there is nothing, the black hole is not causing the mass of the stellar mass to be what it is. It just happens to be the right value because they both correspond to the same sigma. And there's a review of all of what I've said in this annual reviews article from 2015. So what about the assembly picture? I've talked mostly about feedback. Assembly is as simple as it can get. What the authors of these assembly papers said, well, you see galaxies merging. That's how cosmology tells us that galaxies grow. Dynamical friction means that you make the black holes merge, and so galaxies grow and the black holes grow. Why isn't that enough? Well, maybe it is. And here is an example. If you just, the blue square is a load of black hole galaxy pairs, little dwarf galaxies, and you imagine that they all merge. If you just let them merge on average, you will get, just by the central limit theorem, if you make them merge a lot, they will all cluster around a proportionality. And that proportionality can be arranged to be a factor of 1,000 if you choose your seeds properly. So there we had the original paper was 2004. The seeds there, I think, were quite big. They were like 10 to the 7 solar masses. But that was still a lot of mergers needed, 1,000 mergers needed to make a 10 to the 10 solar mass bulge, and 10 times more to 10 to the 11 and so on. So it's not surprising that they all cluster around a strict proportionality in between mass and mass. You then don't have an explanation for the M sigma. You only have M and M, and you actually have to appeal to Faber-Jackson now the other way round and say empirically galaxies do this, and so it turns out that M is proportional to sigma to the 4th. So you're using that a-causal argument the opposite way. So here you can take different types of collections of seeds. The blue things are the seeds, little galaxies with little black holes. And you can see it doesn't really matter what you choose. You can choose all kinds of distributions of initial pairs. They will always produce, at least for large galaxy masses, a relation that lies on a proportionality with the black hole mass. Okay, so that's the central limit theorem, provided, and of course it relies on the fact that you're using many mergers to build your galaxy. And that's the Faber-Jackson then tells you that sigma is there, and there is almost no physics in this relation, except of course Faber-Jackson does use stellar physics, that the stellar momentum driving going on. So what do we know now? Well, how can we decide? Well, the new development is that the M sigma relation is now measured right down to much lower masses than it used to be. A few million used to be the lower limit, but it's now, there's a recent paper of Baldassari et al., and I think there are others in the works, which are right down at the real dwarf galaxy value of about 10 to the 5. Whoops, I'm going back again. Oh, I'm going the wrong way. That's right. Sorry, going the wrong way. Which way should I be going? Yep. Sorry, gone the wrong way. So, yeah, it's measured down to those galaxy masses, and that's a problem because it means that dwarf galaxies can't have had many mergers, and so there's a danger that you don't get a nice tight relation. And you can see it quite easily if you look at the original paper. Even before the dwarf galaxies were measured, you end up with a huge scatter in your mass, black hole mass, galaxy bulge mass relation, because it didn't need many mergers. And so it reflects the scatter in the original choice of seeds. Of course, you can get around it by making the seeds very much smaller, so you need a lot of them again. But there is a limit to that process. And as we'll see, there is another. So it's now, oh, why is this going backwards? Oh, here we are. Here we are. That's it. I think I repeated myself. My slides seem to have repeated. There is something worse goes on, because the Faber-Jackson relation, that is the relation between the star masses and the velocity dispersion, is no longer sigma to the 4th. It actually has been known for a long time that it goes like sigma squared, much more like it. And so if you now use the M is proportional to M relation that you got from feedback, and then say Faber-Jackson gives me the sigma relation, you don't get sigma to the 4th, you get sigma squared. And that is catastrophic, and is not, that's wrong. We can clearly see. Here is the latest galaxy sample, or I think in Baldassari et al. And you can see the caption tells you everything. This is from a paper I wrote with my collaborator, Rebecca Neelan, who I should have mentioned at the outset. The M sigma relation, as you can see, is that those are the data of Baldassari et al. But the M sigma squared relation is the orange line, and the blue dashed dot line. Sorry, I'll read my own caption better. the M sigma squared relations 8 and 9 are predicted by the assembly picture is actually the orange line, which goes way above the points and has the wrong slope. And the black solid curve is the original M sigma relation given by feedback. And so that does go through the points. That's exactly what the Baldessari paper showed. So you can see there's something badly wrong with the assembly theory here. It simply doesn't work. So it does not work for dwarf galaxies. And the remarkable thing is that the relation between the supermassive black hole and the galaxy mass is now no longer linear, because remember, one goes like sigma to the fourth and the other goes like sigma squared. And so the black hole mass should go like the square of the bulge mass. And that tells you something, which now you can see that is a pretty reasonable fit. That's equation 10, which is going through the points. And the blue line there is an older fit of a straightforward linear relation from larger masses. And so you can see it's too high and it's too flat. So the quadratic one does seem to go through the points quite well and has the right sort of slope. So what's causing this change of slope physically in the relation between the Faber-Jackson relation for dwarf galaxies? Well, I think the reason is related to the fact that as you look, if you eliminate, you find that the bulge mass, the mass of the black hole divided by the bulge mass is going like the bulge mass, and of course that means it's smaller. So the black hole mass is smaller relative to the bulge mass at small galaxy masses. The galaxy is all bulge. And so the stellar feedback that fixes the total galaxy mass MB is not getting rid of enough of the gas of the galaxy. It's actually forming stars instead. And there are papers, and I cite one there, which do consider how works in dwarf galaxies. And because of their low gravity, what tends to happen is that the hot gas is able to burrow out in directions that are not radial. That actually gets rid of a lot of the hot gas. And that means that the sweeping out of gas is much less efficient. And so much more of the original dwarf is left, even though there's feedback going on in the center. And that's why you end up with this flatter relation. The other thing that's quite important is that dwarf galaxies are now also observed to have AGN outflows. Remember, the things that were going at 1,000 kilometers a second in big galaxies, if you use the same equations, you find they're going out at about half that speed, 500 kilometers a second. And this paper, Manzano-King et al. Last year, 2 years ago, actually found a lot of outflows that look as though they are driven by AGN. Here's here are the data. The arrow there is the M sigma, the predicted velocity outflow relation for the bulge. And you can see that they're all above it virtually. There's one point with a huge error bar, and there's one point with, actually it's 2 points almost on top of each other. It's two measurements of the same galaxy. Down the bottom, that thing is not really obviously an AGN outflow. It's probably something else. So the other measured systems there are all quite high. They're way above the 500 kilometers a second line, and they're more like 700. And the authors observe you can actually resolve these galaxies and see that the outflows are actually getting outside the galaxy into the dark matter halo. So it does look very much as though there are active AGN pushing in the middles of dwarf galaxies. And indeed, the feedback is extremely effective. They're actually very good at pushing the stuff out into the dark matter halo. So I would take from this several take-home points: that the scaling relations between supermassive black holes and galaxies do arise from feedback. They're not from mergers, and they're not a statistical effect. The real reason people got this wrong is that the parallelism between the black hole mass and the bulge mass was the first relation to be found. It was found slightly before the M sigma relation. And it's because it's such a natural thing, people tend to think of it as being the fundamental scaling relation. And in fact, it's not. It appears it's the black hole sigma relation, which is physically fundamental. And the relation between the galaxy bulge and the black hole mass is almost an accident. It's the fact that there are two parallel momentum-driven relations encoding the same dynamical information or similar dynamical information. And that's it. So I hope that was comprehensible. Please ask questions. I'm very happy to answer them if I can. And it doesn't, don't worry if you think it's very simple, it probably means it's very important. Thank you.
Thank you very much for the talk and for being on time, actually. So, yeah. Calliope, would you like to coordinate the questions?
I have another one that starts in 2 minutes. I'm sorry. So just a question. I'll leave the coordination.
Okay.
That's okay.
Okay. Yes.
I see it quite a bit in molecular winds these days, cosmic ray excitation. So this means that there's also cosmic ray momentum exchange, which means that if you were to take into account cosmic rays, okay, we see it more in jetted systems, but even in accelerated particles crossing magnetic fields in the shell, pushed around from the ISM, so you probably have cosmic rays there too. How much do you expect them to change your slopes?
I think if they were big, they would change things. My suspicion is that although they're quite prominent, they're not the main thing that's doing the driving. So, and I think not every galaxy has them, as I understand it. So you want something probably more universal. So you could imagine cases where they were so big they'd mess it up, they'd change it. But I don't think we see that.
I think this is to be seen observation. Perhaps. Okay, thank you. I will have to go, so Maria, I hope it's okay if you take it up.
Yeah.
Okay.
Thanks a lot. Thank you again for being with us today.
I might have a question.
Yes, please go ahead.
Yeah, thank you very much for your very enlightening talk. It's a very, you showed very vividly in very broad picture of what happens with feedbacks. But what happens if you start putting ugly details inside? For example, in the case of, you said about the cooling of the shocks by quasar radiation.
Yes.
You have very hot radiation coming from the quasar, trying to hit an even hotter shock electrons. Now, the cooling cannot be Thomson, must be a little bit Klein-Nissen. Therefore, the rate of cooling should be decreased because of this technical, say, details. And this can be a factor of 3 or 10, maybe, producing, I mean, less cooling than what you would expect. So I was wondering, yes, I was wondering to put all this inside, do you still retain this picture or there are variations because of that?
People have had a go and done this actually in quite elaborate detail.
Okay.
And I think what happens, I think if Klein-Nissen is important, the narrowness of the swept up gas is reduced. It's a bit wider, I think, but essentially the same picture arises. And I think the reason for that stability is if you think about, just the fact that you've got a cold object trying to hit a hot object, and it's always going to cool, whatever you do. The question is, how efficiently does that happen?
Yeah, this is my question. I mean,
and I think it is less efficient, or it can be, but it doesn't really change the picture. I think the whole thing sort of basically works.
Okay.
but it's worth looking at.
Okay, I see two questions.
I've got one, if that's on the score.
Yes, please.
Which is, if we've got a black hole, now obviously we've got our phases of matter, everything from Bose-Einstein concentrate to plasma. Inside a black hole,
I lost the sound.
Sorry, I think I accidentally muted the speaker.
Yeah. I was trying to mute someone else, and I muted Okay, sorry, Joe. I muted you by mistake. Sorry, please go ahead.
Sorry, what I was going to say is that we've got all the hot gas in the accretion disk, which is still gas verging on plasma. But when you go past the event horizon, and you're getting to the point that things are being squirted out of the poles, but what phase of matter would that matter be in, for a lack of a better word?
Once you're inside the event horizon, you don't know and you don't care because it can't have any effect on the outside.
Well, presumably it is getting squirted back out again.
Nothing's squirted out.
I thought that's what comes out the poles, no?
No. In fact, there's, I think I can guess you're referring to this thing right back at the middle where there's a hole up the middle. Let me see. Oh no, I've gone too far. There we are. The green bit.
Yeah.
The black hole is the black dot in the middle. The green bit are the blue stuff is the wind that's being blown away from the accretion disk, which is densest near the middle. But once you get too close to the event horizon, you'd have to lose all your angular momentum to end up going up the axis. And that is very hard to do. You end up in great looping hyperbole, which don't cross the axis very easily, or they cross it, but they won't go up it because they've got too much angular momentum. And those two evacuated funnels are quite important in a different sense. They don't seem to be important for AGN as far as we can tell, but they are important in ULXs. Somebody asked about ULXs right at the beginning of this talk, or before it. What happens in ULXs, these are ultraluminous X-ray sources. They're stellar mass binaries, but they're accreting at very high Eddington rates. They're supplied with matter well above their Eddington limit. And that's difficult to do for an AGN because even if you make the whole bulge fall on it, it isn't very super Eddington. So that's probably why you don't see it so much there. But in a ULX, that number can be enormous. And what happens if you look at the little tracks that are wiggling backwards and forwards, because I use this diagram for both kinds of talks, the little arrows that are going, there are photons which are desperately trying to escape from inside the bulge of wind that is being blown out. And what is likely to happen if the optical depth is bigger than 1 is that they will find those evacuated tunnels or funnels, and eventually they'll just go out through those funnels. But the funnels are very, very to view this system along its axis, the accretion disk axis, not necessarily the black hole spin, because they may well not coincide. They won't in general in an AGN. If you look down that axis, you see nearly all the photons it's emitting, or a large fraction of them, all trying to come out of a tiny solid angle. And if
so is that what gives us our quasar?
No, that's what gives a ULX. A ULX looks as though it's radiating 10 to the 41 ergs from
the ULX?
The ultraluminous X-ray source. They're binary systems, stellar mass binary systems.
Yeah.
And they appear to be wildly super Eddington. People thought they had much higher black hole masses. We now know that they don't. They're just stellar mass objects. Some of them are neutron stars.
Yeah.
So we know that they're stellar mass. And it's this focusing of the, by scattering of the photons that causes them, the ULXs, to look bright in just those two directions along the accretion disk axis. So there's nothing relativistic about that. It's just, it's true for a neutron star, for example.
So, I mean, I always thought that a quasar is stuff getting out of essentially a black hole.
Nothing gets out of a black hole.
Yeah. So we have also two more questions in the chat. So if you would like to
go ahead. Yeah,
proceed. Yeah. So Jean Slight is asking, do you think that primordial black holes and their accretion disks are the propagators of galaxies?
Well, no, galaxies, do you need a black hole to form one? Is that what you're asking? I don't think you do. I think you just, gravity forms galaxies. That's all still under discussion. So I think you don't probably need a black hole. It's not even clear how you form the black holes to start with. It's often claimed that you need seeds. You have to form quite massive objects because otherwise you could not grow the ones that you see at redshift 6. They are a billion solar masses or more, and the universe is only about 1 billion years old. And if you take an incautious expression for the radiation efficiency, you find that you can't grow it very fast. You can only grow it by a factor of 15 or something, E-fold it by a factor of 15. But that's because people let the black hole spin up. They assume it spins up, in which case it radiates 40% of of what falls onto it as radiation. And it's not very good at growing. The Eddington limit corresponds to a very low accretion rate. Whereas if the spin stays low, then the efficiency is lower, is a few percent. And that means that the Eddington limit corresponds to a high accretion rate, and you can grow them actually from a stellar mass. So I think that suggests to me, and the reason why you would keep the spin low is that there's no reason for it all to be lined up and just spin in one direction. Gas is coming in from all directions to the black hole, and it goes round, it orbits around the black hole in all directions. And there's no reason for it to always point in the same direction at all. So the black hole spin is probably flipped around and decreases a lot of the time, doesn't really grow. So that I think just gravity you need. I mean, black holes are gravity, but there's nothing special about them being gravitational. So I think it's just gravity that grows galaxies.
So hopefully this addressed Jim's question. And there is one more by Stephen Schreier. Do you have any thoughts about hypothetical dark matter and dark energy affecting the development of small mass black holes? Thank you for the excellent technical presentation.
Thank you. That's an interesting question. People often wondered if black holes could be made, or at least started off by dark matter. And I think the trouble is, since we don't know the properties of the dark matter very well, that's not a very easy question. What is absolutely clear is that most of the mass that's in supermassive black holes at low redshift, in other words, the present day units nearby, most of that was ordinary matter that radiated as it fell in, because that's the Sultan relation. If you add up all the background radiation in the universe, and you for example measure the X-ray background, and then imagine that's made of quasars, then that's telling you how much radiation the mass that built the quasar puts out. And so Sultan did it the opposite way round. It's a suggestion by Paczynski, in fact, what he did was take the X-ray background and turn it into a ration of mass per galaxy. And that tells you that there is, on average, about 10 to the 8 solar masses per normal size galaxy of stuff that must have fallen into a black hole. And so most of the mass in black holes now is ordinary. It was gas, I think. But whether dark matter had some effect at some point, I think still up in the air, nobody knows.
Okay, thank you. Are there any other questions? If you would like to ask something, either raise your hand or just type your question.
Would it take forever to actually fall in? If time is going to change as you're falling in, would it take forever for you to actually fall in?
No, I think it's finite, but it's your own clock, isn't it? I mean, it's
yeah.
But you can read all about this stuff endlessly, about what you would feel like. I mean, you get stretched by tides for a start, so you run into all that. But I don't know what you would feel if you were being pulled apart by tides at the same time. It's quite hard to tell. But
well, I mean, I sort of see that as a Roche limit, effectively, of black hole.
No, Roche limit, yeah, all right, tidal forces, yeah.
Yeah.
But I think what you actually perceive is happening is different from, coordinate time does this or proper time does that. But I tend not to think about what happens inside the event horizon. I have enough trouble.
Would the bulge, could that be considered to be the Hill zone of the black hole?
Oh, you'll have to tell me what the Hill zone is.
Yeah, sure.
Well, it's the area where moons or satellites can operate. So planets are essentially satellites of stars. So the star's Hill zone is where the planets can be. So a black hole is where the stars can be.
The Roche lobe. It's the bit inside that.
No, you've got the Hill zone, which is where satellites can be before they become too far out.
Exactly, they're outside the. But if you get too close, they're torn up and they make rings.
Yeah, that's the Roche limit.
Yes.
The Hill zone is the other one.
Yeah, maybe this discussion is a little bit technical. If you.
Well, I'm not getting it, so it's my problem.
Yeah. Yeah, if you don't mind, I would like just to ask a more general question.
Sure.
Yes, so you described in a very nice way the origin of the M sigma relation and how it applies also to dwarf galaxies and the more massive ones. So I was wondering, because to me, that I'm not an expert in the field, it looked like a very clean picture, the one that you painted about the explanation of the M sigma relation now from the physical point of view. In your opinion, what are like the still open questions in this field? I mean, do we really understand all the details of the M sigma relation, or are some of the dwarf galaxies do not obey some of the things that you have presented?
There's still plenty of things we don't really understand properly. Even basic things like whether Compton cooling really does work that efficiently are sometimes disputed. If, for example, the electrons and the ions are only coupled by Coulomb forces, because all the energy is in the ions and the electrons are the only things that get scattered. So if there was no connection, scattering wouldn't help you. And if you simply assume Coulomb interactions, that doesn't work. So there must be, you would separate into two fluids and it would affect the whole picture. But as people always say when they're asked this question, I remember Mitch Beagleman asking me, what happens if it's two fluid? I said, well, they don't necessarily, the electrons and the ions don't necessarily get the same temperature. And he said, but something else will make it do it. which I think is the general result with plasmas. It's very hard to keep the electron and ion temperatures different because of micro instabilities in the local distribution functions. So that's one example. The cosmic ray thing that was raised earlier, that's another example. How the molecular outflows actually behave, again, people are getting there, but there's still quite a lot of work to do there. So no, it's not a completely settled question, but I think it's fairly clear it's feedback. I think that would be surprising if it's not that. There are still people who, I think Andy Fabian, for example, suggests that at least some galaxies, it's radiation pressure acting on dust that causes this to happen. Again, I think I would have trouble with that in a lot of these cases. For example, when you form the black hole, it forms out of a lot of gas. And the first thing it does is indeed radiate and try and push this gas away. And the gas will be pushed away and it will go optically thin about the place where the warm absorbers actually appear. So they may be leftover remnants of when the black hole formed or began to grow rapidly. So I think there's still quite a few questions left. We won't run out of the job.
Okay, yes, thank you very much for the nice answer and the complete answer, actually. So, does anyone who didn't raise a question would like to ask something? Our speaker? I don't see any other questions. Okay. Okay, so since we don't have other questions, I would like to thank you again once for coming and giving this very nice presentation. I hope that it was also very useful for our students in the audience.
Good, I hope so too.
Yes, and we would be glad also, as I said, to have you another time in the future to discuss more about
Great, thank you very much for inviting
other
me.
aspects. Thank you very much.
Bye.
Bye.
Thank you.